Okay, so welcome back, and let's get started. The topic this afternoon is statistics. So I'm going to give you an overview of different concepts used in statistics, because you'll see that a lot of those concepts are used quite extensively. You guys able to see this properly or not? Yes, you have trouble seeing it there or what? Okay. All right. So this is a general sort of outline of what I'm going to talk about. What is statistics, and this concept of population and sample. And it's very important to know the type of data that you'll be dealing with, and what is probability. Okay. And one important concept is the Bayesian inference, which I will talk about toward the end of this lecture. So the reason I wanted to give a lecture on statistics without assuming that you all know about it. I'm sure you all have had some courses in statistics. I see blank faces when I start to discuss statistical methods, and I've been teaching inverse theory for a long time. But as soon as I start to talk about statistical concepts, I see people are completely lost. And you've seen comments like statistics was my worst class in school. And then there are these, statements like there are three kinds of lies, damn lies, and statistics. Okay? So doesn't matter what you hear about, but the main point is that there is a need to be competent in statistics. You always hear about statistics, and you're yourself always talking about statistics. Like if I were to ask you, like, so how many boys are in the class and how many girls are there in the class? You can say that, oh, on an average, maybe I have 20% girls in the class and 80% the boys, right? So it's things like that are always being spoken at different times. So it's kind of important that you are aware of some of the very important concepts in statistics, because you're always bombarded by statistical information and arguments. And some of those have questionable merit. So statistics is defined as a branch of mathematics. This is used to summarize, analyze, and interpret a group of numbers or observations. Statisticians always talk about data. They go out collecting data. We also go and collect data. So there's no surprise that we want to learn statistics. So it is the science of how data is collected, analyzed, and interpreted. So data is information. As you already saw in the previous lectures, that we have some data D, and we want to find out some information about our model M. We didn't use statistics in the methods that I talked about so far. We use physics there directly, right? But you could also use statistics, and I'll show you how we use that. So typically, the data takes the form of observed measurements, right? So it could be like continuous measurements, continuous values or floating point numbers like height and temperature. So what's your height? You can say that my height is like 2.67 meters or something like that. And so what is the temperature today? It's like right now it's 85 degrees Fahrenheit. Okay, so you guys talk in terms of centigrade, but it's 85 degrees Fahrenheit or 85.5 degrees Fahrenheit. It could be 86 degrees Fahrenheit. But then the data could also be descriptions like dog, cat, the color, the gender, like male or female, and animals like dog, cat, and so on. So this is a very important slide. Data can be classified into two different types. One is the categorical variable, categorical values, and other are numerical values. So what are categorical variables? So let's say that you want to describe the weather, right? So how do you describe the weather? You can say that I want to use temperature. So what is temperature? Temperature could be anything. Right now it could be anything between 80 and say 90 degrees Fahrenheit, right? So all possible values between 80 and 90 degrees is what the temperature value can take. On the other hand, if you want to describe the weather as rainy, sunny, cloudy, then what happens? These are categorical variables. Because you can say rainy is a symbol is 0, sunny is 1, cloudy is 2, right? And there's really nothing in between 0 and 1. You always say 0, 1, and 2, and things like that, okay? Similarly, in practical applications, when you have some data set, rock properties, so is it shale, is it sandstone, is it shaly sand? So these are all categorical variables. On the other hand, the density of rocks could be 2.6, 2.7, 2.71, 2.70001, and those are all numerical values. Now, depending on the type of variables that we have used, we have different distributions and different methods. Like what I talked about in the class yesterday was linear regression, right? But in linear regression, the values that we were dealing with were all numerical values. There is another type of regression where we're talking about categorical variables, and that will be called logistic regression, okay? If I have time, I will also mention this to you as to how we do that, okay? Okay, so statistics starts with data. So we talk about population. So population is the entire group that we're interested in, okay? And I'll show you in a second what that means. Now, sample is a subset of the entire population, okay? And this is called an observation. We work with samples because the entire population of interest is not available to us. Now, in the United States, there's always some prediction right after voting, like who's going to win. And this also was done in India. So that is not done by talking to the entire population. They just collect some samples. They ask people, who did you vote for? Did you vote for BJP or did you vote for Congress? And assuming that people are telling the truth, they look at the statistics and then they make a prediction. Now this time, many of the predictions came wrong in India, right? So that could be biased sample, because they talked to only people who thought a particular political party will win. So this is one other important thing. That's why people sometimes don't trust in the statistical inference, okay? So sample is what we deal with. It would be nice if you could talk to the entire population, right? But that is not possible. So here is a picture that shows you this population, and this is the sample. So now, given this particular picture, let's say that you want to come up with a distribution like what is the ratio of male and female, right? And if the number is very, very large, we take some samples, and then based on that sample, we say that this is the population, right? This is the percentage. And you all know that this could be wrong, because depending on how the samples were collected. So it's very, very important that you are careful about how you collect your samples. Okay. Now everybody has my code that I gave yesterday. It was on linear regression, and there was a random number generator, right? So in statistics, we use random numbers a lot for good reasons, which you will see pretty soon why that is so. Now, have you ever wondered, so how do you generate random numbers? You call your function, right, rand or rand2, but have you ever thought about how that function or the algorithm works? See, computers use something called congruential method. So this is a sequence of pseudo-random integers. Remember this particular term pseudo. Pseudo means not really true random numbers. So what they do, they generate numbers between 0 and n, where this n is the highest integer that you can have in a computer. What dictates what is the highest integer? Bits, right? So 2 to the power n minus 1, n is the highest number of bits that you have. And then the random number is generated from this formula. So they actually go in there. I won't be able to write if I go to full screen. So given a particular number, it predicts this number using recurrence relations. So there are two factors here. One is, these are the two factors. One is called the multiplier and the other is called increment. And there is this mod operation. And I'm sure you all know what mod operations is. Mod of A1, A2 is A1 minus integer of A1 by A2 times A2. And A and C are positive integers. So this is a very simple formula that is used to generate random numbers. And the limitation of this is that this random number generator is controlled by this big N. After this n number of calls, random numbers are repeated. Okay? And that is why these are called pseudo-random numbers. They're not truly random. So larger this n is, you get better random number generator. Okay? But nowadays, there are better algorithms where they have some mixing of these different calls to improve the accuracy. But overall, you can never be entirely random. Okay? Pure random. So what is a random variable now? Now that we talked about random numbers, random variable is the one that is the outcome of a random experiment. And like tossing a die or flipping a coin, you have heard about this in your basic statistics class. And the outcome of a random experiment is called a sample point. And the set of all possible sample points is, say, uppercase S. An event A consists of certain collection of possible outcomes. Okay? Now comes probability. Okay? So what is probability? How many of you know what probability is? Everybody knows, right? Tell me what probability is. Go to me. What do you think probability is?
It's a process to predict how the chances of
outcome, right? And how do you calculate that? Let's say that I want to find the probability of heads in tossing the coin, right? How do I find out the probability?
Number of occurrences by total samples.
Okay. So he said that you flip the coin large number of times,
And then see how many times you got heads. And take that number, divide by the total number of trials, and that's your probability. Right? That's one definition. Okay, very first thing that you want to know is that there are axioms of probability. is that no matter how you define your probability of an event should always be greater than or equal to 0. It cannot be negative. Now, the probabilities of all the events should sum up to 1. Okay? So these are the two axioms that you have to satisfy. So now let's look at the definitions of probability. This is the one that two first benchers gave, right? Say that I have n be the total number of possible outcomes of an experiment. If n sub a of all these outcomes, the event A occurs, then the probability of A is NA divided by N. Okay? We normally hear about this definition. And then we say that provided that the occurrence of all the events are equally likely. Right? If you have a coin that is sort of tampered with, it's biased, then during the experiment, then that is not valid, right? So it kind of makes sense. This is our classical definition. Is anybody asking question? Are not able to see there? Are you guys able to see the screen properly? Okay. So there is a big criticism of this definition. They say that this argument, this definition is circular, since equally likely also means equally probable, right? To start with, you are saying that everything is equally probable, right? So this definition is then it got some flaw. So it was corrected by von Mises in 1957, and this is called frequentist interpretation of probability. So what he said is that the probability of event A is NA by N, the limit that N goes to infinity. Okay? So the concept of equally likely events is completely avoided, and they say that a trial is used to mean repetition of experiment under identical circumstances. Okay? So if you say that the events are equally likely, then you are actually defining probability, but they're saying that why do we do that? We should be more specific, and what you say is that a trial is used to mean repetition of an experiment under identical conditions. Okay? So then there are, again, this is not free of criticism, because you say that you want to do a large number of trials, infinite number of trials, but your number of trials is always finite. And one big problem with this particular definition is that you cannot provide any meaning to the probability of a hypothesis. If you have a hypothesis, how do you assign probabilities to that? Okay? So then we have another definition of probability. This was provided by Reverend Bayes. Reverend Bayes says that probability is a degree of belief. Okay? So the probability theory can be viewed as an extension of deductive logic. So in this interpretation, the degree of belief is a personal degree of belief. Okay? Or an expert's opinion. So if somebody has lived in Dhanbad for many years, and if he tells you that there is around 50% chances of rain today, then that would be considered as a Bayesian probability, because he is giving this definition, this probability, assigning this probability to you based on his personal degree of belief or his own expertise. But he or she cannot violate the axioms of probability. If that person says there is 50% chance of rain, then the chances of not having rain must be 50% also. Okay? So these are different, particularly there are two sort of interpretations of probability. One is frequentist interpretation, another is Bayesian interpretation. And this is like two religions. These are like two religions, and they fight with each other. The Bayesian guys don't like frequentists because they say, oh, you guys talking about frequency hypothesis, but you cannot basically try, run your trials infinite number of times under identical conditions. And then the frequentist guys will say, oh, Bayesian interpretation, you were just talking about experts' opinion, but my opinion can be different from another guy's opinion, which is perfectly all right, but you can always criticize that, right? So anyway, just wanted to run this by you. And then probability distribution. So this basically assumes a finite number of values for each random variable xi, and this is called a distribution function. So we have different kinds of probability distribution function and density function. So here what I'm showing you are, you can see that there is open circle and there are squares, okay? So this is your, these are your probability distribution, and this is your distribution functions. Distribution function is the cumulative distribution of the probability values, okay? So what is normal distribution? A normal distribution is something that we work with all the time, and it's nothing but it's a bell-shaped distribution, right? And the peak is your mean, and the width is defined by the variance or standard deviation. And where did we get this term? Why this term comes in front, this multiplier? Come on, somebody should be able to tell me that. How did you get that normalization term? So if you take this and integrate between minus infinity to infinity, that gives you sigma times square root of 2 pi, right? So you divide by that such that it's equal to 1. Why do you need this to be equal to 1? Axiom of probability, right?
Some of the probability should be equal to 1. Right?
Okay, so this is how it looks like. This is the Gaussian PDF. Gaussian and normal, the same thing. Sometimes we call it Gaussian, sometimes we call it normal distribution. So normal distribution is defined by two parameters. One is the mean, and the other is variance or standard deviation. Okay, only two parameters define the entire population. Okay, so I will skip this central limit theorem and all that. What I'm going to talk about. So there are some other distributions like student's t distribution. Okay, so let's say that M is a normal distribution, 0 mean, and one standard deviation, and V is a chi-square. Then the t distribution is basically M divided by square root of V over N. And I'll explain to you what this means. Now this is called student's t distribution, and there is a reason behind this. The person who actually invented this was not allowed to publish the paper because he was working somewhere. So he published this paper in a pseudonym by student. His real name was not student. So that is why this is called a student's t distribution. So if you look at then another distribution that we'll be looking into is called Laplace distribution. Now Laplace distribution is absolute value of x minus mean of x divided by this b, which is a scale parameter, sort of looks like standard deviation, right? if you have the Gaussian and then you just simply take the square root, this is what it looks like. So this looks close to
the top of the argument of this looks like what kind of norm? L1 norm, right? And
normal distribution, the argument looks like L2 norm, right? So normal distribution is associated with L2 norm, and Laplace distribution is associated with L1 norm. Okay? Okay, so these are some curves you can see in my notes. Now for discrete or categorical variable, we use binomial distribution, for example. If the number goes between 0 and 1, then we use binomial distribution. Okay. Now I'm going to have to talk to you about multivariate distribution. I told you about univariate distribution. When there was only one variable, you can define what the normal distribution looks like. What if you have multiple variables? And what is the joint distribution? There you define something called covariance. Okay? And this covariance between two variables x and y tells you how the variance of one is affecting the other. Okay, and I'll show you this in a second. So a multivariate normal distribution is given by this. So what you see is this x is a vector where I have a vector of some variables. So this x is now x1, x2, xn, for example. And this mu is also a vector. Mean is also a vector. And this mu is nothing but like mu1, mu2, and so on. You have n variables, and each variable has a different mean. And what about variance? What we do is we define our variance using a covariance matrix. So this covariance matrix actually has like sigma x1, x1, or you can say sigma x1 squared. Then we have sigma x1, x2, sigma x1, x3, and so on. And then we have sigma x2, x1, which is same as x1, x2, sigma x2 squared, and so on. So there is this diagonal term which gives you the variance of each of these variables. And there are terms which are in the off-diagonal components. And these off-diagonal components basically tell you how one is related to the other. And sometimes what we do is we normalize those and calculate correlations. Okay? And this is a normalized number. And that also shows you the dependence of one with the other. Okay? So here is an example of multivariate normal distribution. So here we have an off-diagonal term. This is a function of two variables. Okay? So here in this case y1 and y2. And each one of these has the same variance, but the covariance, off-diagonal covariance is 0.8. So now you can see what the distribution looks like. And when the covariance is 0, then these are independent, right? So this is your, now this looks like a circle now, depending on what the variance of each one of those is. So you can, now if you make this one minus, what would that look like? If you make this one minus 0.8, it will look more like that, right? So by changing this covariance term, you can change the shape of the distribution. Now, one other important thing that you want to know is when you have a plot like this, what you notice is that if you pick a value of y1 here, y2 here, this is your corresponding y1. Now if you want to go here, then you can get this value, right? Here you do the same thing. Let's say that you are here. So based on these figures, you can actually tell, like, changing one is whether the changing one parameter is changing other or not, okay? And whether they're dependent. And the covariance term actually shows you how dependent they are, covariance or correlation term. Okay? So this is our standard distribution. Now I have to talk about conditional probability and Bayes rule. So let's assume that I have two events, A1 and A2. And the probability of A1 is PA1 and probability of A2 is P of A2. So probability of a particular AI is sum of probability of sample points in A divided by the sum of probabilities of all points in the sample space, right? So we normally use this symbol PA1, A2 to represent the joint probability, okay? So from there, we will define something called conditional probability. Conditional probability of A1
Occurrence of both the events together.
This is basically telling you the joint distribution. Okay, so that tells you, like, if you want to look at, yeah, this will tell you the occurrence of A1 and A2 with a certain probability. You're right, yeah. But when you talk about, so the joint distribution is giving you the probability of, say, two variables together, right? Now you want to say that, now you want to ask this question, but then tell me, what is the probability of A1, right? You cannot define the probability of A1 without specifying A2 because they are dependent. And that is called the marginal distribution. So this is how we define probability of A1 given A2. Okay? So probability of A1 given A2 is probability of A1, A2 joint distribution divided by P of A2, which is the marginal distribution. Okay? Where you have integrated out the effect of A1. So P of A1, A2 is P of A2, P A1 given A2, and P of A2, A1, P of A2 given A1 is P of A1, A2 divided by P of A1. So now we can basically write it for general multivariate distribution, like I have x as a vector and y another vector. So P of x given y is P of xy divided by Py, okay? That means P of xy is P of x given y times P of y. Similarly, I can define P of y given x is P of xy divided by P of x. So that gives me P of xy equal to P of y given x times P of x. Now these two are the same, so I can put them together, and now I can get an equation that looks like this. P of x given y is equal to P of y given x times P of x divided by P of y. Okay, this is the Bayes theorem. So what is the big deal? This is the Bayes rule. The reason it's important is that this has been used widely in data fitting and different kind of inference. So what we have here is P of x given y is P of y given x P of x. So let's say that I have my data D and I have model M. Okay? This is my observation and this is my unknown. And we talked about the data being noisy. So it is probabilistic, right? So if we use a probabilistic framework, what we're interested is in finding the probability of M given my data, right? So probability of M given my observation is then going to be probability of data given M times probability of M divided by probability of D. Okay? So what is this? What is this then? Well, first of all, the left-hand side is meaningful. All that we're saying is that I want to know the probability of a given model when I have some observation. Okay? So this is called posterior probability. And this one, P of M, is independent of any data. Okay? So that's your prior. Somebody told me that how do I constrain my solution, right? Remember in the deterministic case? And we said you can give it an a priori model. In statistical framework, that will be, you'll have to give a distribution of your prior. And given a model from this prior, what is the likelihood of matching your data? Is P of D given M. And this is called the, yes. Right, so for this is, the model is different for different problems. So let's say that you are doing a seismic inversion problem, right? And let's say that you are interested in finding the probability of velocity given some amplitude, okay? So you say that my velocity can be between, say, some V mean by V max, okay? And I don't know how much I trust on this, so it's a flat distribution. So that's your prior. Then what you do is you pick models from this distribution, generate data, and compute this likelihood, okay? And that likelihood function can be like this. So when you combine these two, you have that. So that then tells us that your answer is somewhere between here and here, and this is the highest probability of the velocity. Okay? So what have we done here? We have started from some knowledge about the system. We collected some data, and this data has helped us to update our knowledge about the system, which is the velocity. So this part brings in the information about the contribution of data in updating your knowledge. Okay? So this is very, very important. And so there are two types of methods that we use for seismic for geophysical inversion. So inversion, what I talked about in so far before this talk was deterministic, right? And if we use methods based on statistical model, these are your what they call stochastic, okay, or Bayesian method of inversion. So in case of deterministic inversion, you have just one answer. In case of stochastic inversion, you have multiple answers with different probability, and some of those will have very high probability and others will have low probabilities. Okay? So Bayesian analysis is quite important. So you have some knowledge, and then you use the information, you define your prior probability, and then you have new data from a research studies, and that gives you posterior. One very important thing you should remember is that, let's say that you go and you collect some data and you got the posterior probability. So that posterior now becomes your prior. You go and collect new data, then that gives you another new posterior, and that will basically be updating your knowledge that you had earlier. Okay? So that is why, yeah.
Probability of D given N and probability of D. I mean, in our case,
Yes, I will show you that.
Yeah, so those are very good questions, and that's why I brought in another lecture to show you. The same linear regression that we did in the class, you could do that using a Bayesian approach. Okay? Why would we want to do that? Because that will give me probabilities. That means I can get some uncertainties. Okay? Now before I go further, there are some, yes, this I don't need some. Okay. Now let me go to the Now this is a full talk on linear and logistic regression. So I will go through some part quickly, and then I'll go to the statistical part more in more detail, because we've already discussed regression. Okay, just to refresh your memory, we have data xi, and y, and then what we do here is we fit a linear model, and a linear model will look like this. Okay, and then we minimize an objective function which is called loss function, and then we try to find the best solution. Okay, so we have used analytic method. So this is your x is your x vector, this is your y vector, and this is actually your G matrix equivalent, and that's your loss function. And we showed in the class that we can get it by least squares. Similarly, we can have this kind of order of polynomial, and we talked about those. So I'm going to skip that. That was L2 regularization, and we talked about this already. So this is one figure I hand drew, but this is what I meant yesterday when I was talking about how to choose the model complexity and also the regularization weight. So this is your training data, which is blue color, and this is your test data. And what you see is that you can make your model more and more complex, and that will basically give you less and less error, but it may not do the same thing with the test data. So when the test data error increases, this is where you need to stop, and that's your model complexity that you want to use. And similarly, you can also
number 3. Like at third order, would you stop at 8?
So in this case, any number between 3 and 8 would be good.
So which one can you choose? Like 3?
I would go in between, because there is some small difference here. Because as long as you are not overfitting, it should be good. Okay. So now here what we have is, again, you can do the same thing with the regularization parameter here, rather than so this is the same thing we do. Okay. So now coming to the statistical view. Okay. So we have this model where I'm computing y using this deterministic equation, A0 and A1. Okay. So these parameters can be estimated from any given sample of data. Okay. So we can think of this as sampling distribution because each sample pair will result in different estimates of A0 and O1. Okay? So since there is noise in the data, I can modify my model to look like this with some noise in here. Okay? Now this noise, for simplicity, I'll assume it to be zero mean and variance sigma squared. Okay? It does not have to be, but just for demonstration for the simplicity of algebra, I'll write it like this. So what it means is that Y is a sample drawn from a normal distribution with mean A0 plus A1 xi and variance sigma squared. Okay? And I will assume that the sigma is same for all data points. So this is your E1, E2, and E3. And that's your line. Okay? So that is my model. So now I will then start with formulating this. So this will basically address your question, for example. So given any data set, we have x1, y1, x2, y2, xn, yn. And if I assume that those are independent, then the joint distribution is a product of marginal distributions, right? So here, this is a Gaussian, right? So then, what is the expected value of your data given a particular model? Is this, right? Yi is your observation, and this is your model with variance sigma squared. So that's your likelihood function. Okay? Now, the product of all of these will give you this likelihood function. So likelihood of y given x, or likelihood of d given m, which is the same thing. I keep changing the notation, but don't get confused. Y and x and d and m, the same. So you have this likelihood. I have not talked about prior yet. So this is just a likelihood function. So given the likelihood function, you really need to know what are the mean values of alpha 0 and alpha 1 and what is the variance, right? So, or otherwise, we can also think about it as, given this likelihood function, I want to know the model that maximizes the likelihood, right? So this will be called a maximum likelihood method if you do that. So how do you find the maximum of the likelihood function? The maximum of the likelihood function will be given by the maximum this, right? Now, what does that mean? This will give you a very interesting thing. So maximum likelihood, or the maximum of the likelihood, will be given by a minimum of this function. Doesn't this look very much like your L2 norm? Right? What is the difference? Come on.
There's no square roots.
There's something else in here. Don't question. Variance. Fantastic. See? This one. What is this thing?
This is assigning some weight to the data. And this sigma can be different for different data points, but for simplicity of algebra, I just kept it the same. So, looks like we really haven't done anything new, right? Because all that we have done is this, and we're saying that this is my Bayesian, not Bayesian yet, it's a maximum likelihood approach. However, there is a difference, big difference. And the difference is that once you have the mean and the variance, you can assign probabilities to alpha 0 and alpha 1. So this will give you uncertainties in your estimation, okay? Which is not provided by the deterministic inversion. So here, one of the things that we assign is plus minus 2 standard deviation, right? And we say that we have 95 percentile within that. Why do we say that? This is because if you take this Gaussian and if you integrate it between minus 1.96 sigma to plus 1.96 sigma, that gives you a number 0.95. Okay, so 95 percentile and plus minus 2 sigma is the same. So you can see that whenever we get an answer, we put some bars, and those are like 95% percentile. Okay? Okay, so now the Bayesian approach. We talked about maximum likelihood, and we didn't have any prior. So here I can bring in a prior probability, just like what we did before in the definition when we talked about Bayes' theorem. And I still have this likelihood. So this now is my posterior. So what is Bayes' theorem doing here? What Bayes' theorem is doing is modifying the prior with the help of the likelihood function. Okay? So if we assume Gaussian error in data, which I already showed, so multivariate distribution, we can have a probability distribution looking like this. And if you also assume that my prior is Gaussian, then I can define it like this. This W would be same as M, but I use W because it's what is used in machine learning. Okay, so using your notation, P of M given D is proportional, no, it's not proportional, is equal to, I have to change this, P of D given M times P of M, and your P of D given M is proportional to e to the power of M e to the power D minus GM transpose CD inverse D minus GM. Okay? And this is P of M, which is proportional to e to the power minus M prior, which is actually the mean, Cm inverse M minus M prior. Okay? So your likelihood is Gaussian, your prior is also Gaussian, and you have a linear problem, GM. So your posterior is also going to be Gaussian. And we have analytic form for this. So you can write the posterior as this. And so you can get the posterior mean model and the posterior covariance matrix. And that's your answer. Are you guys lost? Remind you, this is not going to be true for nonlinear problem. For nonlinear problem, your posterior is non-Gaussian, and for that we have to use different methods. For linear problems, we have to do this. So what is the advantage of doing this? Let's say that for this straight line problem, I have no observations, right? If I don't have any observations, then all of these straight lines, infinite number of straight lines are possible, right? If I have one observation, then I have still infinitely large number of straight lines that are my possible answers, but all of them should pass through that point. When you bring in more points, then they start to cluster up together. Okay? And this is something that you could not do using the deterministic inversion. Remember that problem I showed you? Now if you solve that problem using a Bayesian approach, you should be able to draw a cloud of a possible answer. If you know, if you assign some some variance to the data. Okay, so in the Bayesian approach, then we have the mean, we have the covariance, these are the posterior, so I can actually assign all of these. Okay, yeah. So this is it. Then you have two approaches. One is your linear approach, where you have, well, first of all, your inverse problems, you can have a deterministic approach, and you have stochastic. Other way of doing this is linear and nonlinear. And then we will look at optimization, which is local and global. Okay? So what we have described so far is deterministic and stochastic inversion only in the context of linear problems. So what we will do tomorrow is look at nonlinear problem and deterministic inversion. And then I think day after tomorrow we will look into stochastic methods for nonlinear problems. Okay? In the first half, and then we'll delve into machine learning. So tomorrow I will talk about optimization methods, local optimization methods, and then show an example of seismic inversion, wavelet estimation, post-stack inversion, pre-stack inversion. And then tomorrow evening at 4 o'clock, tomorrow late afternoon, we'll have a lecture in the department, and you all are expected to attend that. This will be on full waveform inversion. That's an example of large-scale inverse problem. And that inversion has been applied to many fields, not just geophysics. It can be applied for civil engineering problems, medical problems, medical imaging and all that. So we'll give you an overview of that method. So this is an open seminar for the whole school, and you are all expected to attend that. Okay? So that's all I had, and right on time. So if you have any question, let's try to have some discussion. I guess you have some other program lined up with Soman. Soman is going to take you around to see some labs, right?
And here there is an observatory visit to after the team will move from here to visit the object, seismological object. One of the how the data are collected, we can see that. Yeah? Okay. Questions, comments, suggestions. So looks like you guys are really interested in this.
I find it very difficult to convey these concepts to the students because they get lost in the deterministic religion.
How can we apply it in that when we are doing some analysis?
Yeah.
How can we apply all this theory?
Yeah, you can apply those. So, 1 week is really a short period of time to talk about both inverse problems and machine learning and give you enough exercise. Like just one example, one exercise took a long time. I have all of these, assignments, and there is one particular assignment where I ask the students to do a solve a linear problem, but with a Bayesian approach. So I'm not sure if I have time to do that, but if you guys want to work on it in the evening, then I can just give you the problem, and you can, whoever is interested, you can work on it and talk to me. But this is not be considered as a regular assignment because we have packed schedule for the lectures. And then I'm also getting some requests to add a few things, which I'm adding, okay? So yeah, I will bring in that particular exercise, and I'll just post it. I'll give it to Soman to send it around. Okay. Okay.
Maximum of the posterior.
Maximum of the posterior
is highest probability. It's like the best model, right?
So in case of maximum likelihood approach, you told about this marginal distribution, that independent variables are jointly that marginal distribution.
No, that was a general statement when we talked about this. I just wanted to show you using independent Gaussian distributions, but they don't have to be. So that was just for simplicity of algebra. And then here, when he came to the full Bayesian, I put in the covariance matrix. That means they are not independent unless it's a diagonal matrix. So yeah, so when I talked about independent distributions, they're not general, but I just wanted to explain the concept using that. Okay. Yes.
Multivariate distribution, we have shown only x and y. What if we have more variables than these two?
It's not one variable. X is n number of variables and y is n number of variables. It's a vector, right?
Time series of it.
Yeah, so x can be a whole bunch of numbers, right? So all of these are included here. So this is for multi-dimensional, so it's for all kinds of variables. I mean, it doesn't have to be one or two. Because I wrote this as a vector, that means I have n number of entries, n number of n variables. Okay.
Suppose if you have a three-component data, x, y, and z.
So what you do is your vector S will have x component, y component, and z component. Okay. But then you have it at multiple stations, right? So you can say x1, y1, z1, x2, y2, z2. Okay, so this is all contained in this small boldface small x, because that represents the vector containing all the input. Okay. Okay, anything else? Yes, please.
Like when you're dealing with these multivariate distributions, like is there any chance of, like, suppose if you're saying that x is having three components, right? Then we should have the conditional probabilities of x given yz, y given xz, z given xy. Right? So, like, is there any chance, like, the conditional probability of, suppose, like the probability of one variable is not Gaussian, like, suppose.
Yeah, so this is an important question. Bayes' theorem does not restrict you to Gaussian distribution. Okay? I put those Gaussian distributions because it's easier to understand and mostly variable residues. But Bayes' theorem is general. You can have any kind of distribution and still works.
So, like, we can use one distribution for one posterior, and I mean, one conditional probability, and like, and we can club.
Sure.
So one question, I'm not sure whether it is right or not. Covariance matrix, how we, estimate?
So this is a very difficult question, because in theory you have covariance matrix where you have the dependence, and so how do we assign that? And this is where we get criticized, that people use Bayesian method, because we typically don't know that. The only way you can know this is if you have multiple repeated observations, and from there you can see the dependence of one on the other. In some problems you do have repeated elements and you can have an estimate of this. In other places you just put those based on your expert knowledge. So defining the prior covariance matrices are what frequent distributable It is about patience. Okay.